Hi, my name is Brian Powell. I'm currently enrolled in the fall 2020 session of Math-32 Statistics, Section 10, discussing Section 12. And today, I'm going to be talking to you guys about variance. What's the difference between sample and population? I guess before we get into it, let me go ahead and shrink myself here. I should first explain what variance even means. So variance, sorry, let me get that out of the way. There we go. Variance, which is usually referred to with the symbol or the lowercase symbol of sigma squared, mathematically means it's the squared value of your standard deviation of a data set. Now, to put that in English, that means that variance is a numerical value that represents how far each data or each set or each amount of data you have from a set differs from the average of that set. So let me explain it with an equation here instead. As you can see, we have two different methods of calculating variance. You have the population method of variance on the left and the sample method of variance on the right. Population refers to your samples as a whole, as in every possible sample in the universe. So, for example, if you were doing a survey on the height of every person in the world, that means your total number of samples will be around 8 billion, rounding up, give or take, which in that case, that means your n here would be 8 billion, compared to sample, where say, instead of using 8 billion different data sets, or 8 billion different sets of data, you would instead have, say, 1,000 from random places all around the world. That would be this lowercase n. So first, let's go over the equations on the left. This top left equation here, mu represents the mean, and mean in this case is equal to the sum of all your points of, again, everything that applies in the universe, all divided by the number of all those data points. Then to get your variance, it's the same method where you're dividing by the total number of data points, but instead your sum is going to be made up of each value you find by your average and then squaring that value. The same concept is pretty similar to sample data or sample variance. Again, average is the exact same, but to find the variance, the big difference you want to note here is that you will be using the number of samples that you're evaluating. So not the total number of samples in the world, but again, say like 1,000 out of the total. And you would also be subtracting that total by 1 right here. To properly show you the difference between the two, here's an example. So let's say that we were going to calculate let's rather evaluate the height of every single tree in a forest. So let's say in this forest, there's 3,500 trees, but for a sample, we'll only evaluate 10. So first, let's do the population variance. Population variance is right here on the left again. So for the sake of example, let's say that you counted every single height of every single tree in this forest. So out of the 3,500 trees, if you added up all those heights and then divided by 3,500, you get 172.3 feet, theoretically. From there, you can calculate your variance with the equation mentioned before. Each point subtracted from the mean squared divided by your total number of trees would give you a variance of 818.7. Now let's compare that to a sample variance. Sample, our sample mean here is our 10 samples, which are right here, divided or all added up and divided by 10, which gives us a total of 163.1 feet. From there, we find our variance with the same method mentioned in the last slide. Again, each of these points, so 121 minus 163, 200 minus 163, 142 minus 163, and so on, all squared, and then divided by 10 minus 1 or 9. that gives us a variance of 812.5. So as you can see, the variance differs ever so slightly when you use a sample. However, it's not a very large margin as long as you're keeping, one, a decent amount of samples to evaluate, and two, they're randomized so that they properly represent the population as a whole. Now you can see why this could be useful in certain situations where if you did a whole population sampling or you did a whole evaluation of a population, while it would be nice to get the most accurate data, it's also an extreme waste of resources. So going back to the example of having checking the height of every single person in the world, that means you would have to evaluate over 7 billion people, which is almost impossible to do. So instead, what researchers can do is they can do a sample of that population, and as long as it's a large enough amount to represent the whole and is randomized, you'll get values that match almost identically to as if you did it over the whole population. Here are my references shown here, and that's pretty much everything. Thank you.